So we have a discussion session now, which I think is going to last for about 20 minutes. So the virtual floor is open for anyone who wants to ask a question to any of the three speakers about their talks that maybe you didn't get the chance to ask before. So please, if you have a question for any of the three speakers or a topic that you would like to bring up, raise your hand. I will also say, please remember if you use the chat to put all panelists and attendees, because I've seen a lot of messages for field talks have been crossed, and some go only to the panelists and some go to the panelists and the attendees. So I think it's a bit of a cut conversation that is happening on that end. So just to get the discussion started, I think I would like to go to some of the questions that were written on the chat that we didn't get a chance to talk about. So Pierre, maybe we can start with you. I just collected some of them. So there was a question about the longer wavelengths for planet formation, right? And there was a clarification from Lokesh afterwards saying that in early stages of planet formation, planets radiate significantly a longer wavelength. I was wondering if these early stages of planet formation could be studied by measuring such an early star-planet system.
I think that's possible in principle if you are talking about young transiting planets. And in fact, this idea of measuring the secondary eclipse depth to get temperatures of the hot side of exoplanets is a fairly standard method. But there may not be many systems that you can apply it to.
Oh, sorry, thank you. There was the question about if there was a limitation of the synthetic fluxes side.
So there are problems with synthetic fluxes. That's why we use this method of taking synthetic fluxes and distorting them so that it's the data that determine the broad shape of the spectral energy distribution. And then the synthetic fluxes are only used so that the function that we're integrating has realistic spectral features in it. So yeah, there are problems with the synthetic fluxes, as we know there are, and so we designed a method that allows for that, so that the flux, the overall flux shape and the total flux that we measure is determined by the data and not the models.
Perfect, thank you. And just the last follow-up, if anyone wants to follow up on any of these topics, please just raise your hand on Zoom. It was about the distortions of the binary members due to binaries, they affect your temperature, and then the limitations towards the low temperature, and is there any, or can you go to end dwarfs?
So the types of eclipsing binaries I'm working on are long period systems where they're very far apart. So the distortion is less than 0.1% for AI phi. There will come a point where your star is not round and there are issues, and those systems are hard to work on, so I avoid them. I work on long period systems where you can assume that your two stars are spheres. So that's not a problem. Yes, you can certainly apply this to cooler M dwarfs, and in fact, I'll repost it in the chat so everyone can see it. But actually with M dwarfs, if you look at M dwarfs that are transit solar type stars, we know enough about solar type stars that we can actually do some nice work on the effective temperature scale for M dwarfs. And I'll post up a recent paper on that in the chat so everyone can see it.
Thank you, Pierre. Then towards the talk of field, there was this whole discussion on the chat that jumped back and forth between the panelists and attendees. So I think not everyone got the whole story, but it was about the spot filling factor, if that was a saturation mechanism, and what were the implications of that?
Yeah.
Phil, maybe you want to comment on that at the beginning, and then I guess Jim, Steve, Jamie, I think you're all being participants, if you want to comment on that as well.
Sure. Yeah, I don't want to misrepresent people, but I'll try to capture this discussion in this chat. So it'd be interesting to see, as I said in my talk, where is the saturation mechanism? Is it in the photosphere? Is it a deeper, more fundamental thing with the dynamo? And there was a discussion about, well, could we look at the spot filling factor in the saturated regime? Are there changes within that activity saturated regime? Do we see the spot filling factor staying the same, or is it changing within there, which would be very interesting. and there was a discussion about would you see a different photometric variation across that regime, and so if the spot filling fraction is constant, then the degree of photometric variation would naively be the same. However, the size of the photometric variation depends not only on the spot filling factor, but the distribution of spots. And so I think we agree that it's a good idea to investigate this, but I'm not entirely sure the way to go forward. I don't know, Jim, if you want to jump in.
I was just wondering if anybody had seen that correlation. You just correlate X-ray activity or photometric modulation amplitude with Rossby number, and does that photometric modulation plateau with Rossby number, or is there still a trend?
I know the data exists. I know Elizabeth's data certainly contains the amplitude of photometric variation, but I don't actually know the answer on the top of my head.
I see Elizabeth Newton has her hand up, so I think she wants to comment. Elizabeth, please go ahead.
Yeah, in my data, I did look at rotation periods as amplitude and did not anything, but I think it would probably be worth revisiting that with the data on hand, and since I did not look at that with back to Rossby numbers at the time. And I know there has been some other work, and I'm looking on the paper, but was one recently that was looking at amplitude as a function of cluster, as a function of different clusters. And showed some similar behavior to the traditional rotation activity relationship. But unfortunately, I can't remember what that actually is.
Thank you, Elizabeth. And following up on other questions for Phil, I think you were asking about the titanium 1 lines. Shouldn't their depths be temperature sensitive too? And how temperature sensitive are the equivalent widths?
Yeah, so that was one of the interesting things about these lines, is that, of course, absorption lines are temperature sensitive. But across and I'm trying to remember why this is. I remember looking at models of these line equivalent widths, so not measurements, but just spectral models. And across the sort of middle of the M-dwarf range, so M2 to M7 or so, the equivalent widths actually don't change very much. And it's very curious, and I made a plot at some point. I don't think it's in my paper, but I think I showed it at one of our lunch discussions during Exostar. It's actually quite flat, and I suspect it's some perhaps coincidental combination of the pseudo-continuum being dominated by H2O lines, maybe canceling out the temperature effects or something like that. But it was surprisingly flat. Now, as you go to the really late M-dwarf, so M7, M8, then it started to take off and get much deeper with temperature. But it was surprisingly temperature insensitive. If I can, I don't mean to change the subject, but I do want to say, Ruth, that was a very nice talk, and I'm very excited about getting ages for the M-dwarfs in the activity saturated regime, because we tried to do that using alpha enhancement as an age indicator and failed because of Zeeman enhancement. And so if we could get the ages of M-dwarfs in that saturated, that saturated curve, we get these ages, we could figure out how long are planets subjected to these X-rays. Is it 1 billion years? Is it 5 billion years? How many X-rays has TRAPPIST-1, C, D, and E, these in the habitable zone, how long have these planets been inundated with X-rays? And we really don't totally know the answer. I mean, we can estimate it's like 3 billion years, plus or minus 2 billion years, but I think that'd be a very exciting project.
Yeah, we should do that. I think, yeah, with TESS especially, that's going to be something that's very, pretty easy to do. Like once we fill in the rotation periods for mid and late M-dwarfs a little bit more, then we'll be able to get really good kinematic ages for those stars. At the moment, that regime is still a little bit sparsely covered. And so ideally, we want a few more rotation periods down there. Assuming you are talking about mid and late M-dwarfs, actually TRAPPIST-1 is so late that it might be even too hard with TESS. But early M's we could already do.
Thanks. I actually wanted to ask you, Ruth, about the sample you were using. I might have missed that, but how were the stars selected?
I used the McQuillan's 2014 sample. There are other stars that I could have added. Angela Santos has a catalogue which includes much more slowly rotating stars and stars at lower masses, and so it would be nice to incorporate those as well. But yeah, for now we just used McQuillan 2014. So 35,000 stars, and about 10,000 of those had RVs from Lamost and Gaia. And the other 20,000 we actually inferred vertical velocity using Bayesian inference. They didn't have RVs. That's what I meant by when I said you don't actually need an RV to use this method. You can infer three-dimensional velocities without RVs as long as you have good proper motions.
Thank you. And well, as I said before, if there are questions from the audience, please just raise your hand. I asked actually the three speakers of today in advance if they wanted to put forward some topics for discussion, and they were kind enough to actually say yes and send some. So I just want to show you that and see if our speakers can give it. We're going to start backwards, so Ruth will go first. With the discussions questions that you had, if you want to start with this, what are the best upcoming prospects for calibrated gyrochronology, and when is it more useful to provide a catalog set of parameters, and when is it more useful to provide software for calculators? You will always provide both. So please, Ruth, if you want to begin the discussion with that.
Yeah, I wonder if, I don't know, I feel like maybe I want to start with the second question first, which I really asked because, you know, we sort of, up until recently, simple polynomial models or simple sort of separable power law relations were good enough for gyrochronology, we thought. And then we got data from Kepler in K2, and we started to see more and more that actually those simple empirical relations don't describe the gyrochronology relations very well. And so now we're moving into this regime where we have to use something more sophisticated, which means we can't just provide people with equations in papers. We have to provide code. We have to provide software. And so, you know, for example, the Gaussian process gyrochronology relation that I showed in my talk is like all very well and good that I've calibrated that. But until I actually provide software for people to use it, it's not actually very useful. And so I guess I'm interested in what people think. Like, would it be more useful for me to actually provide a catalog of ages that people can sort of use straight out of the box? Would it be more useful for people to have access to a Python library that where they can calculate their own ages, or both? I guess ideally we'd have both things, but I'm just sort of curious what people think about this topic.
Thank you, Ruth. Any comments about that? Any ideas? Any thoughts? Anybody has any preference or reason for it?
So I'm very interested in this. This is Jason Eastman. I've written ExoFast, which is very useful to constrain stellar parameters, as I'll talk about in a few minutes. But I'm interested in both because one, I could just use an age prior to constrain the star, and two, I could actually incorporate your physics, and as that evolves with my, or as it correlates with the mass or radius or other properties of the star, then I could change that prior on the fly and investigate all of those correlations. So I think both would be very interesting from my perspective.
Yeah, I think that's a really relevant point. Models change; they change all the time. That's a part of, you know, the reason why we're all here. And having software that is adaptable is, you know, a catalog's just a snapshot. And so that's another reason why it's, I think, useful to have.
Thank you, Ruth, and thank you for bringing this up. It's actually a very interesting topic. In honor of time, I'm going to move a bit towards the one before, Phil, which is connected to actually a question that I just saw on the chat by Line Hinevan, which is, well, regarding Rossby numbers. Again, these of course rely on theoretical models of the stellar interiors. And what we're trying to test with the observations are often different models. I've never been clear on the apples to apples involved here versus apple to oranges. Comments from anyone?
Yeah, so you could, I mean, yeah, I think you could actually ignore these questions, and I'll phrase a question maybe a little bit differently, which addresses that. So with all these investigations of stellar activity, we're all just dancing around some fundamental property. When we're measuring H-alpha, calcium H and K, X-rays, Zeeman broadening, photometric variation, all of these, except for like rotation period, which is a fundamental quantity. But the other ones, they're all kind of dancing around some aspect of activity. And I think that my last question is the one that I'm more interested in talking about, which is related to the one you asked. What is a fundamental activity signature? Because when you measure H-alpha, when you take a spectrum and you get H-alpha, or you get Zeeman broadening, or you get calcium H and K, or you get X-rays, you're measuring it at one point in time. It's changing in time. If they're flares, they're flares. You may be only seeing one face of the star. Maybe the other side of the star has more spots. I mean, I don't know. And so I think an interesting discussion is what is a fundamental property? What is a fundamental activity property of stars? Is it the surface, the entire surface, you know, the whole 4 pi surface of the star, spot filling fraction, and magnetic field strength? That would be a lot closer to the fundamental parameter than a lot of the other things we're measuring. And to get there, it's difficult because you have to watch the star rotate with the spectrograph the whole time to see all sides of it, and with enough spectral resolution and enough signal to noise to actually pull out magnetic field strength and spot filling factor. But I think that would be closer to the more fundamental parameter. Now, if the dynamo itself is saturating, testing that is quite difficult. There are papers on this. There's a lot of really interesting work modeling the interiors of both M dwarfs and sun-like stars, trying to model this quenching behavior. Are there ways to test that observationally? I don't know. When I think stellar interiors, actually studying stellar interiors, the first thing I think of is astroseismology. Can astroseismology tell us anything about dynamo quenching? I don't know. I'm curious. But I don't know a way to get into the star.
I think, Pierre, Maxted, you have a comment on this?
Yes, I think fundamentally all these things are manifestations of the magnetic field in the star, right, which has a strength in the geometry. And something I mentioned in my talk briefly on the Tuesday discussion session is there's a way to get hold of the magnetic field strength in the photosphere of a star if it's in a transiting exoplanet system or a binary, which is via the limb darkening. So this idea that I floated that we see an offset between measured limb darkening and predicted limb darkening when you measure limb darkening in sun-like stars from very high precision Kepler light curves, and you compare that to non-magnetic stellar atmosphere models. And actually there's been a little bit more work on this now by Alexander Shapiro and his group. They're starting to use Muirhead to generate magnetic stellar atmosphere models for sun-like stars. Well, so far they've done it for the sun and a couple of magnetic field strength, and it seems to work quite well. So that looks like a quite promising route, at least for some stars, in the sort of low magnetic field strength regime of getting hold of a magnetic field strength. And specifically, how is the magnetic field affecting the structure of the photosphere? The limb, basically, it's measuring the gradient of the temperature profile. Whether you'd be able to push that up to apply it to stars which are very active and near that saturation regime where you've got star spots that mess things up. I don't know. But certainly I was interested to hear that you're starting to generate magnetic stellar atmosphere models, and I'd be very interested to see what your predictions are for the limb darkening as a function of magnetic field strength, and we can have a think about whether there might be observed systems which we can use to measure that.
There is a, thank you, Pierre. There is a raised hand by Kevin Dawson. Please go ahead.
Yeah, I have a question related to Phil's third bullet point there. So, we can observe, beyond astroseismology, or along with astroseismology, we can measure fairly directly measures of granulation on stellar surfaces from, Kepler or test-like curves. I wonder if some experiment looking for suppression of granulation amplitudes or something in relation to some activity measure could help to answer this question. Of course, granulation manifests itself at the photosphere, but it's also a manifestation of convection. So I'm not sure if it would help answer that question or not, but just a thought.
I like that idea. I really like that idea. You're the expert on it, though. We'd have to design a survey or find objects in Kepler with enough signal to noise where we could look for some correlations. But no, I really like that idea.
Maybe you should bring it to a Slack channel and discuss it there for the whole audience. I just want to move quickly to the last questions before we go to the lightning talks, which is what Pierre brought up. Pierre, you want to say a few words about this topic?
So as I mentioned in my talk, it looks like this method for using eclipsing binaries to measure effective temperatures could work very well, and there's lots of binaries we can apply it to. So really, it's just to get some input from people on what should we do, next. For what type of stars are people sort of begging for much more precise and accurate effective temperatures, and how good do they need to be? Do we need to push it all the way down to 20, or is there somebody out there for some class of stars who just love some decent effective temperatures, even if they're like 80K? That would be like a big improvement.
And the floor is open for anyone who wants to comment. This is your chance to ask. Jamie, Katja, please go ahead.
Yeah, so I think one particularly interesting place is knowing exactly where the base of the giant branch is. So if you have something that's kind of a subgiant doing the turn up to the red giant branch, knowing an absolute effective temperature for that would help set the scale for the models.
Base of the RGB. Okay, good.
Thank you, Jamie. And then we have Kevin once more. Please go ahead.
Hi, Pierre. So, when Willie Torres and I did a version of this to compare the inferred parallaxes of eclipsing binaries to those measured by Hipparcos and Gaia, we found that we could really quite reliably extrapolate to quite hot temperatures. I mean, indeed, beyond where the peak of the SED is beyond the reach of the available broadband flux measurements. Now, in that case, we were, adopting the literature, effective temperatures, and then extrapolating the atmosphere models and finding that worked well. But I'm not sure if I guess I wonder if the inverse problem that you're trying to address here of inferring the temperatures could nonetheless work in some extrapolative way.
That's a really good point. Is that it seems like a bit of a trick here that you can both use eclipsing binaries to check the Gaia distances and use Gaia distances to get effective temperatures. And the reason for that is that the most sensitive eclipsing binaries, the best eclipsing binaries for testing the 0 point of the Gaia scale, parallax scale, are the ones that are far away. Because if you think about it, if you've got a negative parallax for something, your parallax is wrong. And in order to get the distance to an eclipsing binary, I mean, I'm aware of your work, which agrees, I think, very well with the work that the Orakaria group, Darius Gracic and other people have done. To get the distance to an eclipsing binary, you don't actually need to know its effective temperature. All you actually need to know is the surface brightness of the star in some band. Ideally like K band, where you can ignore extinction. And there are very good empirical relationships between temperature and surface brightness in the K band. So you don't actually need to know the total flux from the star. You just need to know the sort of flux per unit area, which correlates very well with, you know, spectroscopic TF or color or whatever it is. So that's the reason why you can sort of do both things, is that if you want to do binaries as distance indicators to check your 0 point of Gaia, then you work in the K band. You just need the surface brightness, which can be empirically calibrated, and you're working on stars far away where you see the effect of a systematic error the most. And then that's a small correction that you apply when you then look at nearby stars. So just to make another comment there, so yeah, in order to sort of work out the distance to an eclipsing binary that's, you know, 2 kiloparsecs away, you only need to know the temperatures, like plus or minus 100 K or so, which is what we've got already. But here I'm really talking about looking at the ones that are really nearby, catching all the flux and fundamentally measuring the effective temperature and pushing that error down well below 50 K. Does that answer your question?
Thank you. I hope so, because I'm sorry, but we really need to move on to make it in time for the 1 minute lightning talk. Thank you everyone for your contributions to the discussion.